Welcome everyone for the October Grand Rounds of the ENACT Network. And I'm pleased to introduce Yanshan Wang, who will be giving his presentation today. He's an assistant professor and vice chair for research in the Department of Health Information Management, which is here at the University of Pittsburgh in the School of Health and Rehabilitation Sciences. His expertise is in clinical NLP and also in large language models and generative AI. And he has worked extensively in applying these techniques to clinical text data. He serves as the NLP lead for the ENACT network. This working group has produced a couple of papers already, and this one paper that he's going to be talking about today. And this is the one which describes the NLP efforts in the ENACT network, which was recently published in the Journal of Clinical and Translational Science. So with that, I'll hand it over to you, Yanshan.
Thank you, Shama, for the great introduction. Good afternoon, everyone. Welcome to this webinar. And today I'm going to talk about how we integrated the natural language processing within the ENACT network, which is a large national EHR network, and some of the lessons we learned during the process. So this is the agenda for today. I'm going to give an overview of the ENACT NLP Working Group, which is a team of more than 13 institutions that we work together to make the NLP deployment successful in the ENACT network. And then I will go over some methods that we adopted in the NLP Working Group for ENACT, and then how we operate the working group and some of the lessons we learned during the process. And last, I will talk about some of the outcomes from this working group. So first, so why do we need natural language processing? So I'm not, talk about what is ENACT, because everyone, I assume, is familiar with ENACT, which is a large national network of electronic health record. So actually, when we talk about the electronic health record, a large portion of the EHR data is in unstructured format. If you think about it, all those different types of data, like clinical notes, pathology reports, radiology reports, those are all in the unstructured format. So in the first cycle of ENACT grant, we mainly focus on structured data from different CTS hubs. For example, the demographics, lab results, medication, diagnosis, all those type of structured data. And it is a huge effort to make those structured data available in the ENACT network. But based on a recent study, 80% of the useful information actually stored in an unstructured format in the EHR. So for example, the radiology report, pathology report, all those different types of clinical notes. So think about if we cannot use the unstructured text data from the EHR, we lose the 80% of the information from the EHR, right? So that's why in the current ENACT grant cycle, we mainly focus on how to leverage this unstructured text data and make those unstructured text data available in the ENACT network to facilitate clinical and translational research. And in order to make those unstructured data available, we need natural language processing. So natural language processing is basically try to process those clinical data and make those unstructured data structured to facilitate the clinical and translational research. And this is another view of different data elements available in the EHR. So a lot of the data, as you can see in the structured format, like demographics, vital signs, diagnosis code, medications, all those type of data. And many important information, for example, the adverse event, social determinants of health, family history, radiology report, pathology reports, those are all in the unstructured format. And what is interesting through our working group, we learned that a lot of the structured data, when they are stored in the clinical data warehouse, they are also stored in an unstructured format because of the template use of, for example, Epic EHR or different EHR systems. So that's why the NLP, natural language processing, is a key to uncover the information from those unstructured format. And that's why we established this ENACT NLP Working Group within the ENACT structure in this current cycle. And we form a team of different institutions in this working group to tackle this challenge. So there are a lot of challenge to make those unstructured text data structured and make those unstructured data available for clinical and translational research. The first challenge probably well know that is the data volume challenge. So unlike structured data that they're already structured and there's not variant format, in this unstructured data, there are so many different, there are large volume unstructured data. For example, there are a lot of one patient may each day may end up with hundreds of notes during the patient visit, and the medical concepts embedded in those meanings in those notes are also exponentially, different. For example, 1 billion clinical notes may result in 150 billion medical concepts because there are so many medical concepts in each clinical note. And storing those clinical notes and querying those larger volume of data is not very practical when we try to retrieve real-time results from querying the database. The second challenge is the dependency on data specialty. For example, if we talk about some observational study or clinical trial recruitment eligibility study for clinical trial recruitment, we always think about some specific cohort. So the research usually target on specific cohort, and that specific cohort will impact the concept relevance. And when we think about the cohort, the clinical notes available for that specific cohort, the note type also varies. So for example, we have all different types of notes in the EHR system. We may have encounter note type, we may have telehealth note type, we may have inpatient notes, we may have radiology report, pathology reports. And there are so many different types of notes in the EHR. And for a specific study, we usually focus on a particular type of notes. And the third challenge is a vocabulary limitation. So not all the concepts of interest may be present in the standard vocabulary. For example, when we talk about ICD code or SNOMED CT concepts, not all the concepts of interest in the research study may present in those standardized concepts. And if there's no standardized concept in those ontology, we cannot extract those concepts based on those ontology from the notes. And they pose some challenge for some comprehensive analysis that require a lot of manual effort to define those specific notes, specific concepts of interest. So as a researcher in this field, we have known those challenges for decades. And we contacted many CTSA hubs in the ENACT network that has already some existing NLP services and NLP researchers and leaders in those CTSA hubs. And thanks to the AMIA, the American Medical Informatics Association NLP Working Group, for which I have served the chair for the past few years. I know almost everyone, every NLP researchers and leaders in those CTSA hubs. And that is the beginning when we established the ENACT NLP Working Group. So at the initiation, we have a total of 13 CTSA hubs joining us. And in order to work efficiently and effectively, we also break those working groups into several focus groups. We allow each CTSA hub to work on the topic that they are interested in. And another reason that we break the entire working group into different focus group is that this cycle of ENACT Grant does not have much budget room to distribute funds to different sites. So we have allowed those different focus group so they can work on some existing funded projects, but they can extend those existing funded projects to a much larger ENACT network so they can make the impact much broader. So we have established 5 focus groups in the current ENACT NLP Working Group that include a rare disease phenotyping focus group, social determinants of health focus group, SDOH, and specifically focus on housing status extraction focus group, opioid use disorder focus group, and sleep phenotyping focus group, and delirium phenotyping focus group. And for each focus group, we have a development site that will lead the development of NLP algorithms that will be later distributed in the entire ENACT network. And we also have several validation sites because NLP algorithm, every institution have different methods to store their clinical notes, or every physician from different institution also have different styles to write their clinical notes. And the generalizability and the portability of those NLP algorithms are very important from one institution to the other institution. So that's why for each focus group, we paired at least 2 validation sites with the development site to validate their NLP algorithm before the NLP algorithm is distributed in the network. And for each algorithm we included here, we also define the cohort and the node type, as I mentioned earlier, because for almost every specific project, there is a cohort people usually interested in. For example, the sleep phenotyping project, this project specifically focus on patients with Alzheimer's disease. So we have to focus on a context, a cohort of a condition that the NLP algorithm that focus on. And without that cohort or that condition, usually the NLP algorithm cannot be really useful. And for example, for the delirium phenotyping project, we mainly focus on patients with the delirium. So within the ENACT network, a good thing is we already have a framework to define the cohort through the share fee framework. So we can do any site within the ENACT network can define this cohort using the ENACT query, and then can use the ENACT share fee framework to share the cohort definition with any other site that is already standardized. And the cohort definition is the same, identical. The second thing we need to decide is the node type, because there are so many node types, different node types in the EHR system. And we cannot say, okay, we need to extract the concept for all the patients with Alzheimer's disease, from all their nodes, because that's not applicable. That's not practical in practice. So that's why we usually focus on specific node type. For example, for the sleep phenotyping algorithm, we focus on encounter nodes, which are generated from the outpatient setting. For the delirium phenotype, the project focus on the clinical nodes, mainly the inpatient nodes that usually generated from inpatients. And for other focus group, we also focus on some specific nodes. For example, for the SDOH, we could focus on the the nodes generated from the emergency department. So those are the 2 decisions we have to make before we implement and develop the NLP. So next, I'm going to talk about the NLP methods we used in the working group. So the first is what kind of NLP tools we need to use to deploy in every ENACT site. So we actually made a decision based on several factors when we decide on the different NLP tools. For example, we need to determine on the tools that is user-friendly, that is easy to set up and easy to operate at each ENACT site. We also need to consider the performance and efficiency. So the tool need to be, can perform parallelly using multi-thread processing, and also need to be a high throughput processing tool that can process the nodes, millions of nodes, in a very efficient manner. And also the tool cannot consume a lot of computing resources because many sites don't have GPU. right? And we have to make sure that tool can run on an environment that has very low computing resources and allow no GPU setup. So that's why a lot of the deep learning or large language model kind of based tool is not within this scope because that requires a lot of GPU resources. And we also need to consider that we need to have some comprehensive support from the tool developer side because there are a lot of practical issues, for example, programming issues or debugging issues when the site deploy the tool on their local environment. And if we can secure some support from the tool developer side, that will be fantastic. And consider all those, of course, the last but not least is the tool need to be proven effective. It's the best that if the tool already used in some large network. So consider all those different factors. We have decided on the Open Health and Natural Language Processing Toolkit, which is OH-NLP Toolkit. And OH-NLP Toolkit can almost satisfy all the aspects we considered here. And particularly OH-NLP has been successfully utilized in the large initiative, which is N3C a few years ago. So that's why we used OH-NLP Toolkit as the NLP tool for the ENACT network. Okay, so another reason is we also got very strong technical support from the OH-NLP consortium that we have a dedicated developer from the OH-NLP team that will provide a lot of technical support. For example, if one site faces some technical issues, the developer will help us debug the issue and figure out what are the required packages or library that is needed to run the tool. So, so this OH-NLP tool is ontology-driven and dictionary-based pipeline. That's why it has no deep learning-based, deep learning approach. That's why it can run on the low computer resource environment, and it supports the file system I/O epic clarity relational database. So, which is really flexible because a lot of the sites have direct access to epic clarity. So they can populate the data directly from epic clarity into the ENACT network. And some sites, maybe their data is stored in a file system. They can still use this tool to process nodes from the file system and then populate the concepts into the ENACT database. So it is very flexible. And we also provide some Python alternative because the original OH-NLP tool was written in Java, and some sites do not have Java packages installed on their instance, so they may choose to use a Python alternative to the OH-NLP, the Java version. And also because it is written in Java or Python, it can be deployed cross-platform, either it's Linux or Mac or Windows. So they're different for every site. The data workflow is different. So here is just NLP data workflow that we have been used in at Pitt. So at Pitt, we have the data research data warehouse, and all the clinical nodes are stored in the data warehouse. So the first step of retrieving the data is usually define the cohort. So once we define the cohort using the ENACT query, and then identify those patient ID of the cohort. Then we can retrieve the data, the clinical notes from the data warehouse, which is called Neptune Data Warehouse locally at Pitt. And once those data are retrieved, we will store those data in a raw note table, so in a Postgres database. So the reason that we have a specific database designed for the clinical notes is that we have to create an indexed raw note database to make the note processing and querying much faster. So in our original research data warehouse, the Neptune data warehouse, it does not have those indexing available there. So processing the nodes in the original data warehouse is very slow. So that's why we build this tailored, very specific data warehouse to store the raw nodes in our infrastructure. And then we run the OH-NLP pipeline to populate the nodes into the I2B2 common data model. So we use the observation fact table as the table to store all the NLP concepts. So here are some details how we standardized NLP output in the I2B2 observation fact table. So the observation fact table in the I2B2 common data model was already used to store the structured data in this table. And here we reuse this table to store the NLP-derived data concepts. So how to do that? So basically, if the NLP algorithms follow some standardized terminology. For example, if the NLP use ICD ontology or Snowman City ontology, we will build specific structure to store this NLP field in the observation fact table. Follow this structure in the concept CD field. First is the NLP, and then project name, and then vocabulary, whether it's ICD code, Snowman City code, and then followed by the code name. And if this is a customized, because the design principle, the design philosophy of R2B2 is to make sure that we have the flexibility to design all kinds of accommodated model or the concepts. And similar here, a lot of the NLP algorithm actually populate the customized vocabulary or customized concept that does not exist in the ontology. So for example, if one of the project require customized methods, we will just use the custom as an indicator to tell, okay, this concept is really a customized NLP concept. And then we will extract the concept for that specific customized project. For example, for sleep project, all the sleep-related concepts is customized terminology, and then we store the sleep concept in this way. And we also, for the NLP, for every NLP concept, there is also important factor called context, because NLP concept may be negated. For example, in the clinical notes, it may be written like this patient has snoring. And also it could be written like this patient does not have snoring recently, okay? And this negation is also important for understanding the NLP concepts and also understanding the condition for the patients. And related to the context, there are three categories. We call that certainty, whether this concept is negated or hypothetical or positive. So hypothetical means something like if this patient develops snoring, then do that. So this is a hypothetical mention of snoring. And the second category is experiencer. For example, whether this concept is for the patient or for the patient family history. For example, this patient has breast cancer, and the experiencer will be this patient. And in the clinical notes, it may also written like this patient's maternal grandmother has breast cancer, and then the experiencer will be the patient maternal grandmother. So this kind of experiencer of the concept is also important for a lot of particularly cancer and gene-related disease. So we will extract that context as well. And last but not least is the temporality. So whether it's a present or whether it's a history of the patient is also very important. So we will extract all those different concepts, all those different context attributes, and then store those contextual attributes in the modifier CD in the observation fact table. And it's not uncommon that sometimes we need to extract the numerical information from the EHR as well. So for example, for the medication, we want to extract the medication, the doses information, the frequency of the medication from the clinical notes part. And in order to store that kind of information, we use a modifier CD field within the observation fact table, and we use a modifier CD field in conjunction with the vol type CD, T-vol char, and novel num, which are three different fields in the observation fact table to store this type of information. For example, this is if we want to extract aspirin and we want to extract a dosage, we will use the modifier CD to indicate what kind of, whether it's a dosage or whether frequency or whether it's a route, and to indicate that. And then we will use vol type CD or TVol char and invol num, those different fields to indicate what is the dosage number and what is the frequency, whether either it's once daily, twice daily, or whether it's through oral or through different types of route. And we have also developed standardized concepts for each of the field, how to define the medication use. And we also use the observation blob field to store the phrases that and the sentences that related to the NLP-derived concept. So, for example, we extracted this concept from the clinical notes, and then we will store the specific snippet. Most of the time, it's the sentence where these concepts come from. And we make this populating this observation blob field optional to the site because many sites are conservative in terms of populating the original notes in the ENACT database because some of the original notes may contain PHI. So we made this optional to a lot of the sites. And another thing is that currently under development is node type standardization because, for example, the EPIC or many different Cerner EHR systems does not standardize the node type. And the node type really vary across different sites. Right now, when we determine on a specific node type, we will let each site to determine specifically what node type they want to include for that definition. And right now we are developing some node type standardization where we will use SNOMED CT and LOINC code to standardize the node type for all the different size node type. And then we will use those type as the indicator to indicate what type to extract those concepts. Another methods we need to deploy is the NLP ontology, that the ontology need to incorporate the NLP concepts. So specifically in the ENACT network, we develop a specific ontology for those NLP concepts. And those ontology will be stored in the clinical note hierarchy. And then for each specific project, we developed all those different types of concepts in the ontology. And for some of the concepts, if the concepts follow a specific standardization, and then we will use the UMS CUI or some specific code to code those concepts. So those, when the NLP concepts were extracted from the nodes, then we can use this ontology, specific ontology to query those NLP concepts. We also develop a pipeline when a site want to join a specific NLP study. So for example, if we have here, we will have two scenarios. For example, the first scenario, when a site already have an existing NLP algorithm and the site want to deploy the algorithm across the ENACT network, the site will first contact the ENACT core and then integrate and set up the NLP framework and populate those concepts locally from the EHR nodes to the ENACT database. And then they will run the NLP algorithms locally to extract those concepts and then populate the concepts into the ENACT database. And then the NLP, usually the ENACT core will develop the ontology specific to that NLP algorithms and then distribute the ontology across different sites. And then the site will populate those different sites, will gather the algorithm and then populate those different concepts into the ENACT network. And once those concepts are populated in the ENACT network, each of the any site will be able to query the entire network based on the ontology setup and then perform the cohort query and receive the aggregated patient counts from the entire network. In the second scenario, when a site wants to propose and develop an NLP algorithm and then deploy the algorithm within the entire network, the site first need to propose the project to the working group. And then the working group will decide what sites are willing to participate in this project. So we will likely form a focus group and then the site that will propose the NLP algorithm, will develop an NLP algorithm and share the algorithm with an ENACT core and then distribute the algorithm across the entire network. And then we will also assign 2 validation sites to the algorithm and then validate what is the generalizability and the portability of the NLP algorithms before deploy the NLP algorithm across the site. And once this algorithm is validated in the 2 validation sites, then we will distribute the sites across the network, and then the network will run NLP pipeline, populate the concepts into the ENACT database, and make those concepts queryable. In addition to the deployment and implementation, we also developed an evaluation framework because during our process, we found that the intra-site and cross-site validation is really challenging and a lot of time require a lot of resources to validate the NLP algorithms. So to make this evaluation framework more streamlined and more efficient, we actually developed a site-based workflow. So first, of course, we need to make sure that the site that interested in the project will have the notes pulled and manually reviewed. And then the development site will develop the NLP algorithms and then determine the generalizability of the approach based on the testing data. For the second development site, if they join this study as well, they usually will develop the NLP phenotyping algorithm based on the train and the validation dataset as well, and then determine the generalizability approach with the first development site as well, and test the approach on the held out testing dataset. And then these 2 development sites will test the generalizability cross-site. So basically test the NLP, the generalizability on the validation dataset cross-site. And if there's a third development site also interested in this study, we will determine, we will use basically a pseudo silver standard to validate the algorithm because we already have 2 sites validated the algorithm. So for the third site, we will use the silver standard. And most of the time, we will use a diagnosis code or standardized structure code as a silver standard to validate this approach, and then determine the generalizability of the approach based on the held out test set. So this approach has been validated in several studies in the current network and has been proven much more efficient than validated the algorithm using just a manually created gold standard. So error analysis is another common practice in the development and validation of NLP algorithms. So there are a lot of, for example, when the second site joined this study and validate the algorithm on the test dataset, the second site need to further refine this NLP algorithm based on the testing result. So that is also not in the previous NLP pipeline. There's not standardized error analysis pipeline. So in our working group, we also developed this more standardized error analysis pipeline to facilitate that process. So this figure presents overview of the site level error analysis process adopted by our working group. So we use our previously created error analysis taxonomy and also based on the clinical text retrieval and use towards scientific rigor and transparent, in short, the trust process to guide and standardized error analysis. And we focus on identifying four most common error types within the error analysis that include logic errors, linguistic errors, contextual errors, and annotation errors. And the site will focus on these four basic common error types and then refine their NLP algorithm based on the error analysis from those four sites. We also gathered information about the task and the focus area. For example, it's a disease use case or medication use case, and also some of the NLP methodology and annotation details in the process. We utilize this error analysis algorithms during development and then apply the results to enhance NLP algorithm to make sure the NLP algorithm is generalizable, portable, before it is distributed among all the ENACT sites. And next, I'm going to talk about the ENACT NLP operations because we have a lot of sites in our NLP working group, and to make sure that every site on the same page and to make sure that they are deploying the same NLP algorithm or the same NLP pipeline is very critical to the success of our working group operation. And then we also have a very tight timeline to deploy the NLP algorithms across the ENACT network. So we have a monthly working group meeting and also we have a progress chart. So basically we split the entire NLP deployment into around 10 steps. And in our monthly working group meeting, we interact with each of the sites in our NLP working group, and we check what is the progress of each site in this, progress chart. And we also discuss what are their challenges, whether it's technical challenges or whether it's some other challenges. And we will connect the site with the specific person that will be able to address the challenge. For example, if there's a technical challenge, we will connect the site with the OHNLP support group. And if the site has some data access challenge or the instance challenge, we will connect the site with the ENACT, the correct NLP working group to address that challenge. And so far, we are still working across a lot of the challenges here, but we are making a lot of progress here. And to make the communication much easier, we also use the Slack to manage all the communications because a lot of the deployment of the NLP toolkit is very technical. It involves a lot of the debugging and a lot of technical issues. And Slack, will make it much easier, to solve site-specific challenge. And we also, as you see here, we also have created a specific channel, which is OHNLP Support Center. So we have a dedicated person from the OHNLP consortium that will support the technical details of the NLP toolkit. So some of the lessons learned, deploying the NLP across the big network is not a trivial task, and we faced actually many challenges. And there are a lot of lessons learned, but here are most importantly some lessons. For example, high volume and structured data. So whenever a site want to join our working group, the site usually is struggle with the high volume of unstructured data, and sometimes we have to navigate how to downsize, for example, how to make this cohort definition more strict, or how to select this appropriate number of clinical note types to make the project more practically doable. We also face some limited funding and resource constraint because some sites, there are some projects they are interested in, but they do not have enough funding or enough resources to deploy the algorithms or to deploy the algorithms. And there are a lot of data variability across sites. I will talk about this in the next slide. There are a lot of implementation delays and site-specific challenges because every site is different. The way they, for example, the way they get the unstructured text data from their local infrastructure is very different. It varies a lot, and we have to tackle with a lot of these practical challenges. And last but not least, there's also lack of a theoretical framework for implementation. So in our working group, we just do a try and see what implementation works best for the entire working group. But there are a lot of theoretical framework in implementation science that may benefit our working group, to deploy this NLP algorithm. So there are a lot of, as I mentioned earlier, there are a lot of challenges, site-specific challenges in the NLP implementation. So our most critical lessons learned was that the data heterogeneity across sites. And even within the same EHR vendor, we still face a lot of fundamental challenges. So, for example, we found that most of the sites, 9 out of 11 sites, use Epic as their primary EHR system. And we encounter substantial heterogeneity in implementation of the Epic EHR system. And each site use different data access sources. For example, some sites use the Epic Clarity as a data source. Some sites use OMAP. Some sites use their own clinical data warehouse. And each of the unique resources may come with some unique challenges, like the template variations across departments and the time periods, loss of formatting during the ETL process, and inconsistent use of the structure fields and the site-specific documentation workflows within those sites. So, and a lot of sites also demonstrate very different, a lot of diversity in how the clinical documentation was structured and stored. For example, at the University of Pittsburgh, we have a dual Epic Cerner environment. Our inpatient is documenting using Cerner. Our outpatient is in Epic. We require a lot of pre-processing on those nodes generated from Epic or Cerner. And another institution like MUSC, Medical University of South Carolina, face a critical ETL process where the structured significant formatting issue. For example, the tables, new lines was stripped during the data warehouse transfer. Actually, we have similar issue here at the University of Pittsburgh, and some other institutions like University Alabama Burlington UAB, they have a Cerner system, and they have a lot of PDF formatted EHR text, and they have to do a lot of the OCR technique before using the data. A particularly unexpected finding was that the structured assessment templates were often exported as unstructured text blocks. For example, this is a very universal finding from our study, like UT Southwestern, their risk screening templates, the UT Health Sciences, Cerner's, their nursing flow sheet, and University of Kentucky's nursing assessment. The data was all structured, but they all appeared as narrative text data in the EHR. So those issues require developing a lot of pre-processing and very site-specific pre-processing code to process the data. But the good thing is because we have this working group, a lot of the pre-processing ideas and techniques can be shared within the working group, so they can develop some pre-processing code efficiently to make those text data available. So last, I want to talk about some outcomes. So we have formed this working group around more than 2 years ago, and we have actually have a lot of outcomes from the working group. The first is the paper we just published recently in the Journal of Clinical and Translational Science. Uh, we report the development and the deployment and validation of the NLP framework in the ENACT network, and also report all the previous I mentioned those techniques you can find it in this paper. And we also have a lot of specific publication from several focus groups. For example, our SDOH focus group, we published a paper on the housing extraction using the ENACT network. So we reported how we developed the SDOH housing instability and housing issues using the NLP and within the ENACT network, how we deploy this algorithm in the ENACT network. Um, so the lead site was University of Kentucky, and we have 3 participating sites in this study. And another study is from the delirium focus group. This is a really multi-site study. The lead site was University of Texas, Texas Health Science Center at Houston, and they developed algorithm to extract delirium detection using NLP. And then this delirium algorithm was deployed in the ENACT network. And there are 7 or 8 participating sites for this study. Another Another outcome from our working group is to support grant applications in the working group. So a lot of the participating sites, they have many local PIs. They want to use the ENACT network and NLP pipeline in the ENACT network to conduct multi-site study. And most of them are observational studies. So here, I just we have several funded projects. For example, the first one is a K Award funded to the UT Health for the delirium cohort. They try to deploy the computational phenotypes of cancer-related cognitive impairment in old adults. And also the second one is from the same site. They have a funded project for the delirium as well. And we also have several pending grants that within the fundable score. For example, this one, we have a project try to use the ENACT and NLP to study the precision rehabilitation using the pipeline in the ENACT NLP. And we have several sites, participating sites from the working group as well. Last but not least, I would like to thank the NCAT and also the OHNLP consortium and all the sites that participate in our ENACT NLP working group. Without those site commitment and contribution, all those results, all those outcomes won't be possible. And we're also onboarding several other sites right now. For example, the Morehouse School of Medicine, we're also onboarding them into the ENACT NLP working group. And we have several other sites that are interested in this working group. We are onboarding them as well. Thank you, and happy to answer any questions.
Thank you, Yanshan. I mean, that was a very comprehensive review of what the working group has done, and it looks like it's been really successful in doing several projects. So I'll open this up for any questions, and we can unmute you if you have a question. So while we are waiting, so Yanshan, how many of these sites are there any sites using anything other than I2B2 at this point?
Yeah, so many sites actually have OMOP and retrieve their data from OMOP. And some sites retrieve the data from the Epic clarity directly, and some sites retrieve the data from the clinical data warehouse. And they have this I2B2 and ENACT instance. And actually, interestingly, some sites, their I2B2 and ENACT instances are separate, managed by separate teams. So yeah, every site are quite different.
But is there any site where the destination for the NLP concepts is going to be, say, OMOP or CDM?
No, most are.
Most are I2B2. All
Yeah,
these are I2B2 at this point, with the
right,
destination.
right.
Okay. Let me see if anyone has any questions. So in terms of the standardization for storing these concepts, the, you come up with a standardization scheme. The working group has come up with this for I2B2 that you showed us. Now,
Yeah.
uh, is can that be sort of extended very easily to OMOP or CDM if they are connected to the ENACT network?
I know in OMOP, there's also OMOP NLP Working Group, and they are working on some NLP efforts to populate the NLP concepts in the Node NLP table in OMOP. So a lot of, I would say, because the design philosophy of OMOP is different from I2B2, some of the standardization methods, it could be translated into OMOP, but it need some significant change. Yeah.
Okay, there's a question in the chat. I'll just read it out, and I think I can answer part of this. How does ENACT compare? This is from Paulina. How does ENACT compare to PicoNet in terms of structure, data model, and intended use for AI or learning health system research? So interestingly, the predecessor of ENACT, which was ACT, when NCATS funded the network, they asked us to be compatible with the PicoNet model. So in terms of the data elements, which are available in the sort of the ACT data model, which sits in the I2B2, and the PicoNet data model, they are pretty much compatible. In fact, I would say ACT has probably got a superset of some of the data elements because PicoNet, depending on the site you're in, has restricted number of data elements and certain things like labs and so on and so forth. But they're pretty compatible. And then in terms of the use, so ENACT was originally set up to basically get back counts for queries that you run on structured data. So basically, it is counts of patients in terms of satisfying inclusion-exclusion criteria for studies. And those counts can also be used for some simpler kinds of research. But to do any deeper kind of research, including AI-based work, you really need to have patient-level data. And on both PicoNet and ENACT, the way that gets done, at least in ENACT, the way that gets done is there's ephemeral enclaves which are available now. And people can suggest a project. Once the cohort is defined, then the data from the sites which are participating in that project, the data gets moved to a AWS environment in UC San Diego. And then there, the environment allows you to do all kinds of analysis. So that's a work in progress so far. So we have to update the data governance and data use agreements at each of the sites to enable us to move data out to the enclaves. So far, 4 sites have signed on that, and there's about a dozen projects which are using data from those 4 sites. But slowly, it'll be rolled out to all the other sites so that we can access data from the other sites. Okay. See any other questions? And I think Yanshan, you're planning to do also some sort of enclave project for NLP purposes.
Yeah, yeah, right. So the idea was that we developed some NLP algorithms and then populated those concepts. And a lot of the concepts was actually used in the downstream predictive modeling or some AI models as additional features. But how those AI models or predictive models, how generalizable they are from side to side is actually understudied. So we try to use the secure enclave provided by the ENACT to basically use those structured data as well as the NLP features to test those predictive models because we have the capability to get the data from the network, and we will be able to evaluate those AI models and predictive models, the performance across different sites using the pipeline, the NLP pipeline we built. So, which is really understudied right now. For example, the healthcare system, when they want to deploy sepsis prediction models, how does that model perform on their local environment? So, and how that perform, if one healthcare system develop a sepsis prediction model, they want to know how that perform in another institution in a different population setup. So we will be able to test that kind of performance using the ENACT network and the NLP pipeline we developed.
Jake, do we know what's the next grand round?
Yeah. So appreciate everyone joining today. We have our next grand rounds, I believe, is on Monday, December 1st with Dr. Philip Payne from WashU. His presentation is titled, I had it right here, Artificial Intelligence and Clinical Transformation, Accelerating Research, Learning, and Practice. So I think will be an interesting series with the last couple of talks and this talk as well. And we'll send out more information to the broader listserv for that soon.
Okay. Okay. Thank you all for attending this grand rounds, and with that, we'll wrap up.